All right, welcome everyone. And thank you for taking time out of your obviously very busy schedules to be here with us. We have a very cool event lined up where we'll talk about how we managed to cross the barrier of 500 gigabits per second on a single Varnish enterprise node. And we have a good lineup here, both people from Intel and people from our own organization. Now, for housekeeping, we see that all of you are muted, so that won't be a problem. But if you have questions, because we'll organize a Q&A near the end of the session, if you have this dedicated Q&A box here in Zoom, please post them when you want, and we'll handle them at the end. Now, if you would have some remarks or things to mention, we also have a chat box, which I will be monitoring throughout the session. My name is Thijs. I'm the technical evangelist here at Varnish, and let's get going. Can I have the next slide, please? So this is some legal stuff that was promptly skipped, but this is the agenda for today. So we have Kleppen, Paul, and Assad to talk about the various aspects of how we reached this or how we traversed this boundary. We'll sketch that background first. It's very exciting. And then we'll talk about what I wouldn't call it the secret sauce really, but how the design of a CDN using Varnish Enterprise and how NUMA awareness, which will be a key component today, really matters. And then Paul will join in, talk about Varnish features and capabilities. And Assad will talk about the NUMA awareness in Varnish Enterprise and how that actually managed to get us there where we really wanted. And in the end, we'll share the benchmarking results. And to top it all off, we'll do a Q&A session. Next slide, please. So let's have a little bit of introduction of our cast of characters for today. I have my colleague, Paul Herman Johansson here. He is a senior developer and product manager with Varnish Software and working on the enterprise product. He has worked with us since 2016 and focuses on working on highly optimized HTTP caching technology. Also my colleague, Assad Ahmed, who has joined us in November of last year. He's a C developer, and he is working on some interesting stuff that you will see here today. And in his master's thesis, he focused on improving the TCP implementation in the Linux kernel, which suits our use case very well. And then, of course, we have Nash. He's a solutions engineer, and he works on CDN technology, CDN platforms, and software performance analysis and optimization. So his help is very welcome here, and these three gentlemen have come up with something really nice. So next slide, please. So I think this is the point where I hand it over to Kleppen. Kleppen, the virtual stage is yours. Thank you.
So just to get started and set some background here, through the pandemic, CDN has seen a huge increase in demand as people are stuck at home more often. And so, for instance, live streaming has really taken off over the past couple of years. Additionally, as higher resolution screens become more and more ubiquitous, the demand for higher resolution content to display on those screens grows. And so if we go from a 1080p stream on average to a 4K stream being much more common, that greatly increases the load on a CDN. This has also been made possible by some technologies becoming more affordable and easier to use. So one of those is 100 gigabit per second Ethernet. With those NICs becoming broadly available, as well as the switches to support them, multiple 100 gig NICs in a server is now quite feasible. And so the goal of this collaboration between Intel and Varnish is to improve the performance of these CDN nodes, either through hardware or through software. And some of this work includes some pre-validated solutions, the Intel Select solutions. There are dual socket versions as well as single socket versions of those. It also includes NUMA and TLS optimizations in Varnish software that results in better CPU efficiency and better performance. And so if we take a look at a sample configuration here, if we look at a 2 terabit per second CDN that we're going to run each node at about 80% load to leave some headroom. If we had systems that could achieve 200 gigabits per second reliably, we would need 13 systems. On the other hand, if we add these new Varnish nodes that we're going to discuss today, that could be cut as low as 6 systems, which naturally consume less space and power than 13 similar systems. And that's possible through software optimizations. So better threading models, more efficient memory management, and improved resource locality. We can also look at this a different way. That 2 terabit per second capacity, let's say there are 310,000 users, and half of them now demand 4K content instead of 1080 content. Well, so the aggregate bit rate grows drastically. We go from 2 terabits per second to about 5 terabits per second. Now, if we were to maintain using those 200 gigabit per second systems, that would be 32 systems. On the other hand, with these 500 gigabit per second capable systems, that could go as low as 14 nodes instead of 32. And so this is an example. It's an artificial case, but it is trying to show the importance of these types of optimizations. And so now I'm going to talk a little bit about CDN system design and how NUMA, non-uniform memory architectures, play a part of that. And so with newer storage servers, we're starting to see some interesting trends. So NVMe storage being the standard is becoming more and more of the case in broadly available servers. And so what NVMe's offer is greatly increased performance. With that greatly increased disk performance, we now have enough disks that in these VOD use cases, we can make use of faster and faster networking. The networking is also getting less expensive and easier to get. So these types of servers are used in CDN, they're used in scale-out storage, things like Ceph. So these systems, when we target higher performance levels, it is fairly common to go from a single socket to a dual socket system. And that gives you more compute density per server as well as more throughput capability through doubling the IO. However, when we go to a dual socket system, non-uniform memory architecture is now something that we have to deal with. It is no longer really optional. And so on Intel processors, the interconnect between the two processors is called UPI. Typically what we see is that UPI will have enough bandwidth to support this workload, but there's a cost, a non-zero cost in latency every time that we cross a NUMA domain when we don't have to. And so avoiding that penalty is very important when we try to scale up beyond 200, 300, 400 gigabits per second. And at lower performance levels, the latency impact is less pronounced. It is there, it does not go away, but it is not as significant. When you start to have more efficient software that can go faster, faster storage devices and faster networking, then it really will make itself known and become the primary bottleneck in some cases. And so to make the most out of these dual socket systems, they need to be designed for this type of workload. And so a NUMA balanced server is critical to get the most performance possible out of a dual socket server. Most of the servers that are available target a more general use case and tend to favor socket 0 over socket 1 so that that server can easily be sold as either both sockets populated or only one socket populated. And so for those not as familiar with NUMA, this is a diagram trying to show what it would look like logically. And so we have, in this case, 2 NUMA nodes per physical processor, and interconnect between those 2 processors, as well as memory and IO devices on each of the processors. And so, what the lines here with the arrows show is that your memory access from any given core could either be local or it could be remote. On average, that'll happen 50% of the time if you have not done anything to optimize. One thing to keep in mind is that a NUMA node and a socket are not equivalent. One socket may have many NUMA nodes. So in the common case, they do tend to be related, but they are not identical things. So if you look at a diagram of a good general purpose dual processor system, what we see is that we can get a NIC in each socket and at PCI Express Gen 4, which is good, but we cannot get the same amount of drives in each socket. And so here CPU 0 only has 4 drives instead of 6. And what that means is as we scale up the load on this machine, we'll see that CPU 0 runs out of IO before CPU 1. In addition to having some performance consequences, that means that CPU 0 will be underutilized. And so money was spent on that processor that we are not able to extract all of the value from. If instead, this processor has, or this system has the same amount of IO on each processor. So in this diagram, 2 NICs and 6 drives per socket. Then we do not have an imbalance in load between the 2 processors, and maximum value can be extracted from both. Also on the topic of system design, there are single socket systems. It's fairly common to see single socket systems that are designed more for reduced costs than they are for extracting maximum performance from that type of configuration. And so in a single socket system, this diagram shows what can be done and what can be found out in the marketplace. So there exist single socket servers that offer this type of configuration where you can get 2 by 16 NICs and 8 NVMEs all running at Gen 4. And so again, this is about extracting maximum value from the processor that has been purchased. And so at this point, I'll hand over to Paul to talk about Varnish and some of the things that make it run so well.
Thank you, Nash. Next slide, please. Yeah, so this is an overview or a simplified picture of Varnish, what it is. And you can see at the top of the slide, you can see some clients. It can be mobile phones, it can be computers, but of course it can also be set-top boxes or TV sets with apps running on it. In the middle, you have Varnish, which is cache. And below, you can see the origin servers. Depending on your use case, you can have many cache nodes or you can have many origin nodes. For example, if you're running a newspaper, you might have many apps and you can have Varnish route and assemble pages based on output from such apps. If you have a large CDN or if you distribute video, you can have just a few origin servers, packagers which produce the video content, and you can have many, many Varnish servers. So this is just one example. And part of the idea here is that you want to scale up the cache, the servers which are optimized for the use case, and not spend all your money on the origin service. Next slide, please. Right, so there's a long list of features that I could talk about in Varnish, but I'll just highlight the few which are featured in this presentation. First of all, we have something called the massive storage engine. It is the component of Varnish which allows having huge caches on disk and serving them efficiently to many clients at the same time. We have in-core TLS, which differs from the open source Varnish, and it's necessary to deliver the data as fast as possible. We have NUMA awareness, which is very important, of course, and we also have a high performance architecture with worker threads. I have represented the worker threads here by some workers. And of course, high performance architecture needs a bit of explanation. So let's talk about that on the next slide. Right, so why is it fast Varnish? We have a highly optimized fast path, which means that when you have the good kinds of requests, which turn into cache hits, we have minimized the number of context switches, typically represented by system calls. We have minimized locking. We have minimized memory copies. So we have a very high focus on performance in general. When we do have to allocate memory, which is also one of the things we try to minimize, we use a very efficient memory allocators, which fit well with heavily threaded applications like Varnish Enterprise. Thirdly, we don't let the kernel interfere with how we do the caching. So the data that we serve is on disk, and the massive storage engine manages this. And instead of letting the kernel's algorithm decide which part of the data is in memory and which is not, we take control by using asynchronous direct I/O to move things into memory and to write the data out to disk. This is surprisingly important when we look at the big picture. We are, as again, NUMA-aware. That's what much of this presentation is about, and we have a good TLS implementation. Nothing revolutionary, but it's relatively good. Next slide, or I guess I'll hand over to Assad now.
Yeah, right. Thanks. Next slide, please. In Varnish, we have the concept of thread pools, and a thread pool is used to partition the work inside Varnish, and this is to reduce the contention and to manage when managing tasks and to accept client faster. And each thread pool usually has one worker, which is acceptor thread, and the work of the acceptor thread is to bring work into the pool, and that it does that by accepting connections. And we populate by default 2 thread pools with 5,000 worker each. And in Varnish, in NUMA Varnish, we pin a pool to a specific node such that we try to reduce the UPI usage between the pools. But we don't try to eliminate it, but just enough that the UPI link does not become the bottleneck. So we try to reduce the amount of traffic that's traversed between the pools. Next slide, please. So as I mentioned earlier, one worker accepts connection per pool. The clients arrive at all available pools and are delegated to an idle worker in that pool. If we have no worker, then the accepting thread reschedules itself and before taking care of more clients. So in NUMA Varnish, we have modified the acceptor thread to only accept clients from the same NUMA region as the origin of the request. So that's usually coming from a NIC. And so in this picture, we see that we have 2 NICs and we have 2 CPUs or sockets, and the NUMA or Varnish will not let connection coming from the left NIC go to the right CPU, so it will keep it in the same region. And this is done by loading a small kernel program to apply socket filtering and based on the NUMA node. Next slide, please. One may think that NUMA node is the same as one socket, but as Nash explained, this is not always true. So newer CPUs come with multiple regions, and the cost to access a remote node usually depends on the distance between the local and the remote node. But the cost to access a remote node is never free. So in Varnish NUMA Varnish, we see this region as isolated, and crossing them is not acceptable. Yeah, next slide, please. So in Varnish, some memories are recycled by threads to avoid too many memory allocation and deallocations. Such buffers are now local to the NUMA node and to minimize the UPI traffic that traverse the UPI link. TLS buffers and workspaces are 2 important examples of this. Next slide, please. So in order to use this, you will need some things to fulfill before you can get started. And that's first first thing you need is the Varnish Enterprise version 6.08 R2 or newer, and you need a kernel that supports reuse port and eBPF program loading, and you need the libnuma library, and finally you need to give Varnish some flags or parameters to say that you want to use the NUMA-aware feature inside Varnish. And with that, I will say that be aware that if you run this on a non-balanced system with, for instance, 2 CPUs but only 1 NIC, it is expected that Varnish with NUMA awareness activated will only utilize one of the CPUs, as there is no NIC to deliver traffic to the other CPU. With that, Nash will talk now about NUMA balanced systems and how they can improve the situation.
Thanks, Assad. So if we're using these new versions of Varnish and we have a optimized system design, we can test it and see how much our results improve over what we were doing previously. And so before we get into the test results of these systems running these new versions of Varnish, I need to talk a little bit about how we're testing, because testing at this level of throughput is not easy. So we're using a software tool called WRK. Many of you are likely familiar with it. And we are coordinating multiple instances of WRK running on different physical clients using parallel SSH to get them generally synchronized. One important thing to keep in mind about WRK is that it will run as fast as it is able. So up to either the networking limits or processing limits. This is different than what we would expect from, say, a single physical client, which is generally only going to pull as much throughput as is necessary to keep the video stream fed. One thing that is different with this workload from what a typical workload would look like is that we are selecting all of our objects randomly. Each client also has its own data set to minimize the likelihood of finding an object in memory and force more reads from disk. So this is a near worst case scenario access pattern. Most of the time, a client that's displaying video wants to watch that video mostly in order, rather than bouncing around in a random fashion. We've selected some WRK parameters, particularly the number of connections and the number of threads, based on feedback from customers, as well as observations that we have seen in using the tool. And so the test cases that I'm going to talk about today are using 256 and 512 connections per processor. These are executed without an inter request delay. There's also a 4096 connection per processor test. However, that has a randomly selected inter request delay of between 115 and 120 milliseconds. And each of the clients that we have can run it up to 100 gigabits per second. And so we're using multiple clients, and that will limit our maximum throughput. So for the single processor configuration, this is what we have. So we're using a Xeon Platinum 8380. And we have that system with 8 Gen 4 by 4 NVMEs, as well as 2 Gen 4 by 16, 2 by 100 gig NICs. And so a maximum line rate on the NICs of 400 gigabits per second. And then we have a DIMM per channel of memory. And with this configuration, this is all able to fit into a broadly available Supermicro server. And so we have that connected to a switch where we have our origin, and we have 4 of these 100 gigabit per second capable clients. And so we ran some VOD testing. And so with this test, we were able to achieve up to 340 gigabits per second out of this single processor with its one CPU. And this is with all of the traffic between the clients and this cache node being TLS encrypted. This is at a 100% cache hit rate with that uniform random distribution that I talked about, and the data coming off the NVMEs rather than sitting in memory. However, these systems do have that memory available. And so that means that we can very easily dual purpose these machines. They can handle this VOD workload, and they can also handle a live linear workload. And so for this test, what we're using is some VCL to identify our live traffic our live traffic will sit only in memory and will not be written to the disks, and will then be served to the clients from there. And so in this case, with this live workload, we were able to achieve up to 366 gigabits per second. In this case, the traffic is also TLS encrypted between the clients and the cache node. And in this case, rather than a 100% cache hit rate, this is a 93% cache hit rate. And the uniform random distribution has been maintained. And so up to 366 gigabits per second is very strong performance out of one CPU on a 400 gigabit per second line rate. In the event that that performance is not sufficient, we can scale this up. And so for this testing, we're using a dual socket system, the same processor, so 2 of the Xeon Platinum 8380s. We're scaling up from 8 drives to 12, but 6 of them per socket. We're scaling up from 2 NICs to 4, 2 of them per socket. These NICs are also 2 by 100 gigabit per second capable. The memory fan out is very similar. The number of DIMMs is increased, but the capacity per DIMM has gone down. This lets us maintain 1 DIMM per channel on both processors and the same memory capacity. This is also using a broadly available Supermicro server. And so with this server, we have an 800 gigabit per second line rate. We have enough drive fan out. And again, just like before, we have this connected to a switch with our origin, as well as now 8 clients, 100 gigabit per second capable clients. So just like the single socket server, we can test this for video on demand. And what we see with video on demand is that we can get up to 487 gigabits per second. And this is possible in large part due to the NUMA awareness features in Varnish. Those allow us to maintain better locality of our data and minimize the amount of times that we have to cross the UPI bus. Every time we cross the UPI bus, that costs some amount, a small amount, but some amount of time. And so that added latency does compound itself and does become significant at these very high throughputs. Another consideration at these very high throughputs is that the Linux page contention behavior that you'll see as your network throughput increases beyond 200, 300, 400 gigabits per second can start to be the limiting factor. And so to minimize that, we have enabled sub-NUMA clustering on these processors, and that splits each physical processor into 2 logical NUMA zones. And so this gets back to what we were talking about earlier, where one physical processor may have more than 1 NUMA node associated with it. And so in this configuration, again, still being 100% TLS between the clients and the cache, we're able to achieve this 487 gigabits per second. This system can also be dual purposed for live linear, the same way as the single socket server. And so in this case, we're just using the memory, and we're able to achieve 409 gigabits per second out of the same server using the same VCL configuration. And again, the cache rate here drops to 93%.
It's 509. You said 409.
Yes, 509 gigabits per second. For those interested, these are all of the details of those configurations. It covers the same information that we discussed on the slides. There's a little bit more detail here, but fundamentally, same information. And for those that are interested, there are additional resources available where you can learn more. There is a white paper covering these configurations and this testing. That is the first link here. There's also a white paper that uses a lower power set of processors to achieve similar results at a lower throughput, but still very strong performance. There's also the network builders page and the Varnish Software web page for additional resources about Varnish and how it can be used. And there are resources for those select solutions that I mentioned earlier, which are pre-validated configurations. And there is also the Intel page for visual cloud and CDN topics. At this point, are there any questions?
So I have a couple of questions lined up here, but I would invite the audience, if you have questions, to put them in the Q&A box. We have the resources there. It's a dedicated tool for Q&A. And I'll kick off the first question is which platforms are supported for the NUMA improvements? Which of our speakers will answer that one?
Yeah, I can take that. So in the NUMA-ready Varnish, we support Debian Buster and Bullseye and CentOS 8 by default, or Red Hat 8, and Ubuntu Bionic and Focal and Amazon Linux. There are some platforms we don't support, but that's due to old kernel or that's usually the reason behind it. But it's usually supported across the platforms.
So let's summarize that. That's Debian Buster, Ubuntu Focal.
Yeah, Buster and Bullseye and Bionic and Focal.
Okay, and then
yes, CentOS 8 or Red Hat 8.
Perfect. Thank you very much, Assad. And then I have another question. Is
one thing to add, in addition to the software support, is that although it will function on a system that does not have NICs on each socket, I would not recommend that configuration most of the time. To get the most value out of the optimization, it's important to have NICs in each of the NUMA zones. That way you do get the improved utilization. So there's the software support side, and then there's the hardware to take advantage of that.
And I see a related question coming in that builds upon this, Nash, is if you want to learn how to do this, like from an architecture and system and administration point of view, is that hard? Is that mentioned in one of the resources you have there on your slides?
The white paper gets into a little bit more detail on how this is configured and how you would replicate this testing if you were so inclined. In general, from a system administration standpoint, it isn't that much more involved than a standard Varnish node. It's just a node that has been configured in hardware more carefully than picking a server at random from a vendor. There's a little bit, there are 2 extra parameters in your Varnish command line to enable the NUMA awareness feature. And then from there, it is a little bit of tuning, and that's it.
Great. Maybe a little reminder to the audience is that the session is recorded. So the slides and the video footage will be available and sent to you afterwards. So if you want to have a look at all these resources that Nash mentioned, you will have the ability to do that. Then I have, there we go. Then I have another question coming in. For 4K videos, a client needs around 25 megabits per second, asks one of our audience members. A server with 800 gigabits per second should be able to handle 32,000 of those clients. What's the achievable throughput at that level? And if there's a mix of SD video clients? So that's a bit of a mouthful, but any of our speakers can answer that. So I'll rephrase the question. For 4K videos, a client needs around 25 megabits. A server with 800 gigabits should be able to handle 32,000 of those clients. What's the achievable throughput at that level if there's a mix of SD video clients? Nash, Paul, Assad?
So I haven't tested that exact configuration, so I cannot say definitively what level of throughput would be achievable or would not be achievable. However, the objects that we're using for this testing were 1 megabyte in size. And so a 1 megabyte file being read off of disk into memory and then transmitted to the client is not outside the realm of what is reasonable for either a 4K video that is being very rapidly sent to the client or a standard definition video chunk that's being sent more infrequently. In terms of that exact mix at of 4K and standard definition clients, that would be something that would have to be tested to really know what that would perform at.
I can add to that a bit. So it's a really good point that clients are not equal. And of course, a client which requests an HD stream is different from a client which just want the standard definition stream. But there are also differences in distance from the server to the client. Maybe someone is on a mobile network and there's added latency and package loss at the connection and so on. The benchmarks, which is carried out by Intel, mainly focus on they focus on clients which are nearby. So of course there will be a cost for maintaining all of those connections in the kernel. But the point of this exercise is that it is achievable to have very high throughput, and then there's no benchmark, there's no bottlenecks when reading from the disk at those kinds of speed or writing to the NICs, but there will be other bottlenecks potentially when you have many clients, and the kernel needs to handle all of those connections at the same time.
And then again, Paul, you probably agree with me on this. It's also a matter of horizontal scalability, of course. So you're not expected to do all of that on a single node. If you have the server capacity for it, you can scale out horizontally.
Yeah, and 800 gigabit is not available. I mean, we have shown 500 gigabits here, and of course you can never reach the line rate, and the line rate is also different from the amount of bits that needs to go to the client, because you have overhead on each of the layers in the network stack.
Thank you, Paul. And I have one more question here, a very predictable question. Of course, all of these wonderful results are presented through Varnish Enterprise, but one of the questions is, like, what can you expect on Varnish Cache, the open source version, in terms of performance? Yeah,
so there are some things which are not present in Varnish Cache. For example, there's no in-core TLS. You do have things like TLS terminators, which help a lot. And with Unix domain sockets, you get a long way. And I think you would be able to be close to 200 gigabits on open source Varnish, but not much more. That's just my guess of this. You also don't have the massive storage engine. So if you want to serve from disk, it's simply not possible to get those kinds of speed. But if you have a live stream use case, you can probably go to around 200 gigabits per second with open source Varnish.
That is a very clear answer. Thank you, Paul. I see that there are no more questions in the Q&A, so let's wrap this up for today. Thanks again for watching this. The video footage will be made available, and I would like to thank Nash from Intel for joining us, and of course my colleagues Paul and Assad, and of course a special thanks to the audience here. I hope you enjoy your day.